Hey gang, STAT 1800. We're going to start confidence intervals today. This is actually some of my favorite stuff to teach. I know that makes me sound like a gigantic geek, but you know, so be it. Confidence intervals. All right, let's step back just for a second. We've seen this drawing ad nauseum where we're examining the relationship between samples and populations. And what we've seen so far, if the information about a population is known, then we can determine the likelihood of getting something unknown from it using probability. Okay, so again, you know, if we have a larger population and we know the parameter values, we can determine the likelihood of getting a sample which is unknown, again, using probability. And an example of something like that would be, you know, we know that IQs are normally distributed with a mean of 100 and a standard deviation of 15. So therefore, my population, my entire group that I'm interested in studying, has an IQ, again, with these parameter values. That is known. But if I was to come in and take one person at random, or 50 people at random, or whatever it may be, I don't know what I'm going to get, hence random. I don't know what I'm going to select. But I can determine the probability, for example, that one particular person chosen at random will have an IQ higher than 120, less than 118, between 118 and 120, all different types of problems, can't I? I can also determine that a sample mean IQ of maybe 20 people from this population chosen at random will have a mean IQ greater than some value or less than some value or between two values. Those are things we've looked at before. What we do today is we change the direction. We change the direction where the population value is unknown, but the sample that we go out and collect to use it to make a statement about or to estimate a value in the population that's unknown, this branch of statistics is called inference. It's called inferential statistics. Now, this vicious cycle here, probability leads into inference, and inference kind of leads into probability. But I want to think about it this way. I want to think about what we've learned in probability is going to lead into what we're going to learn about inference. So again, what's inference? It's taking a sample and using it to make an inference about a value in a population that is unknown. Now, let me give you an example. I think I mentioned before, I love to scuba dive. In fact, as I'm putting up this video, just before I actually put up the video, I was on exchanging emails with a dive instructor down in Puerto Vallarta. So I'm getting ready to go down and here in a few weeks and dive the San Andreas fault line. So I'm really excited about it. There's something else kind of cool. There are these giant manta rays that I mean, they can be 20. I think the largest one they've seen in that area is 27 feet across. It's like a big stingray. So I specifically requested my second dive to be in an area where I've got the best probability. There you go. The best likelihood of seeing one of these things. I don't know what will happen if I get down there and run into a 25-footer. I'll probably freak out, but anyway. But anyway, back to the diving. There are these things called C-fans, and C-fans are just you know, you see these things a lot. These plants. You see them a lot in the Caribbean when I dive over on the east coast of Mexico. I mean, there are places, they're everywhere. Well, the C-fans are coming under attack, and they're coming up with this disease that I can't pronounce. But anyway, biologists are really concerned about this and want to study it more. And essentially the question that they're asking is what percent of the CFANs are infected with this disease. So, the population under study is CFANs, and what they want to know, which is currently unknown, is what percentage of these things are infected by this disease. Well, what they'll do is they'll go out and take a sample. So maybe they'll choose 100 CFANs, and they'll find in that sample of 100 that 28 are infected with this disease. So what we can say here is we can say that 28 out of 100, or 0.28, or 28% are infected. Now, does that mean that we've answered our problem and addressed the issues? No, it doesn't, because what we found out from the central limit theorem when we studied probability is we can take sample after sample after sample after sample from a population. This is just one of them. In fact, if we took another sample of another 100 CFANs, took them back to the lab and examined them for this disease, we may find in the next sample of 100 CFANs that maybe only 22 or 22% were infected. And then we may go out in another part of the Caribbean and get another 100 randomly sampled CFANs and find out that 34 or 34%. So you can see that these samples are likely to vary, and they will, and they're expected to vary. But guys, even though that variation was important when we were studying probability, we expressed that variation using something real fancy called a standard error, we now want to focus on the process in statistics where we take only one sample and use it to make an estimate about the population value that's unknown. Well, guys, again, this is a very, very important branch of statistics, and it leads us into something called inference. And for you guys in STAT 1800, I'm trying to find a piece of paper, so if you hear me rattling around in the background, that's what I'm trying to do. And I'll tell you, I'm not having any luck. I usually have paper everywhere. Here we go. So again, it's very important for us in STAT 1800 to get a really good grasp initially on these things called confidence intervals. Because guys, what we're going to do, we're going to have so many different types of problems in this class. You know, we're going to have problems where we take a sample mean and want to use it to estimate a population mean. We're going to have situations where we're going to take a sample proportion and we want to estimate it, use it to estimate a value of a population proportion which is unknown. So guys, throughout these illustrations, we're going to have values from our sample that are known, and we're going to use it to estimate values that are unknown. What percentage of Americans intend to vote for Donald Trump when he reruns for president in 4 years? I don't know that. I mean, there's really only the one thing we could do. We could kind of predict it or estimate it by going out and taking a sample and using the techniques and the strategies that I'm going to teach you in this class to make an estimate of an unknown value. We're also going to run into situations where we may want to look at the difference between two means and use this to make an estimate of the difference in the population means. Maybe we want to know if the mean ACT for males is different than the mean ACT for females at Shawnee State University. Well, I would go out and take a sample of males, a sample of females, and use this to make an estimate of the difference of the population means. Something else we'll run into. We will run into multiple and simple regression where we want to take values X and Y values and be able to use X values to predict certain Y values. Maybe we want to use a student's high school GPA to predict their first-year college GPA, in which case we're going to run into these things called regression slopes. Well, guys, we will want to use sample regression slopes, which we can calculate from our sample, so it's going to be known to estimate a population slope of a regression model. So guys, STAT1800, I mean, you guys are going to get thrown with a lot of stuff. We're going to get into ANOVA, chi-square, all kinds of applications. Well, not as much chi-square, but all kinds of applications for confidence intervals. So guys, it's important that we get a solid understanding, a solid foundation of these things called confidence intervals. Now, okay, so always keep in mind an important: samples vary, but we use only one of these. So in every situation, we could go in and take multiple samples from a population, but we don't do that. If we did take multiple samples, then they would all be different. They would vary. Not all be different, but we'd expect variation. It's called sampling variation. But we don't do that in inference. We take one sample and use that sample data to make estimates or test claims about values in our population. Now, let's go back to some stuff we know. From the central limit theorem, we know that if we take samples size n from a normal distribution with mean mu and standard deviation sigma, that the distribution of sample means will be normally distributed with a mean equal to the population mean and standard error equal to sigma over the square root of n. Now, we know that we can transfer these, trying to keep it as non-statistical and mathematical as I can, into z-scores. And we know that z-scores have a mean of 0 and a standard deviation of 1. Now, how do we make this transition from here into here? Well, we use the z-score formula, which is taking the raw score minus the mean over the standard deviation. In this case, it's the standard error. That's the way we make this transition from here to here. Now, what else do we know? We know that from the empirical rule that approximately whatever value is at 2 standard deviations below the mean, and whatever value is here, which is 2 standard deviations above the mean, that approximately 95% of our sample means will fall between here and here, which tells me if I come down to this related distribution, that approximately 95% of our values in the z distribution will fall from a z-score of -2 to a z-score of +2. Now guys, that's using the empirical rule, but it's not exactly true. It's a good approximation, but it's not exactly true. So I'm going to turn my paper this way. So an important point that we want to look into right now, since we're getting into big boy, big girl statistics, is when we look at z-scores, again, with a mean of 0, standard deviation of 1. So smack dab in the center here is 0, and then out here we have a standard deviation of 1. But what I want to focus on, between what two z-scores does 95% of our distribution fall between? Well, Guys, it turns out that this is a question that we can work very easily on StatCrunch. So, guys, let me get into... well, I'll tell you what, I'm going to have to get... join SSU. Alright, so let's go get into StatCrunch. So I'm just going to go through my math lab. My wife's Facebook is up, so that's going to be annoying. I'm not near as popular on Facebook as she is. She seems to get notifications like every 30 seconds, and I seem to get one about every 30 days. So, woe is me, right? Alright, let's find your all's course here someplace. Here we go. Alright, going to StatCrunch. Hopefully you're there and waiting on me. Alright, so guys, under stat, we know we have this calculator, and we have this normal calculator, which we can use for z-scores, as we've seen before. And what I'd like to know is between, so I'm going to click that one, with a mean of 0, standard deviation of 1, between what two values do I have 0.95? Now, I'll go ahead and tell you, it's going to be negative 1.96 and positive 1.96. But we can, if we don't know that, we can compute that. You can see it's exactly as I said. So I'm going to write negative 1.96 and positive 1.96 over here. Now, so what I can say, I'm going to keep a running total here, okay? I'm going to keep kind of 3 columns. So I'm going to just talk about percent between. And I'm going to put a 95% there. And my upper level on the 95% is positive 1.96 and negative 1.96. So I know that 95% of my sample means fall between a z-score of negative 1.96 and positive 1.96. Okay? What if, just for some reason, I wanted to know instead of 95% between what two values 90% of the sample means fall? Well, that's going to be pretty easy, isn't it? All I got to do is come back to this drawing and go 0.90 instead of 0.95, compute, and we'll tell you it's going to be, well, let's just see, it's going to be 1.64. Now, this is kind of a tough call here because if I go 1.64, that 0.0049 is right at 0.645. So instead of going 2 places, because of the way this number turns out, I'm going to go 3 places. So I'm going to call this negative 1.645 and positive 1.645. So I'm going to write that here. So negative 1.645 and positive 1.645. Okay? Now, just for the heck of it, actually it's not, there's a whole lot of structure going on behind the scenes here. What if I wanted to get 99%? So instead of 95% or 90%, I want to know the two values, two z values, between which 99% of our sample means would fall. Well, guys, again, very, very easy. 0.99. So negative 2.57, I'm going to call it negative 2.576. And positive 2.576. All right, guys, I'm going to end this video here, and when we, I'll start the next video pretty much right where I end this one, and we will go on with more about confidence intervals. Take care.